Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about inclined planes and ramps and the like. Now this is part of a series of videos that I'm putting together to discuss basically forces, but in some sense like applications of forces. Special forces may be a bad way to say that because it's not special forces in the sense of like Green Beret or Army Rangers or Delta Force or whatever, but like special applications of forces in physics. And in today's case, what I want to look at is inclined planes and ramps, and specifically those just in and of their own case, like without friction, without worrying about air resistance, etc. And we can add those other things in later. So a ramp basically just means that you have a surface that an object is going to slide along, and generally speaking a ramp can have any geometry like this or whatever, some arbitrary geometry. This is a sort of ramp. But I also generally, when I use ramp, mean a little bit smoother of a geometry, something like an inclined plane. So an inclined plane essentially means the ramp is sort of flat, if you will. It's just not horizontal. Okay, so this is a general ramp. This is the special case of a ramp called an inclined plane, or something like a straight ramp or something like that. Most books would just say inclined plane though. And what we want to do is consider what forces act on an object when it is on an inclined plane. Alright? And to get there, we start off with something that is just a flat plane, a horizontal surface, whatever you want to call it. We place an object on that horizontal surface. The object here is at rest. So we know from the free body diagram for the object that there is a downward force. This would be basically gravity, so we could say something like F gravity or mass times g, some object with mass. We also know that the object doesn't just fall through the surface. If it's sitting on a tabletop, for example, it sits on the tabletop. It doesn't fall through the tabletop unless it weighs quite a bit. So we know that there must be some other force that acts upward, and that is what we call the normal force. I usually use an Fn for that. Some sources or some textbooks will use an N or an N to represent it instead. So in this case where you have the object sitting on the horizontal plane, on the flat surface, whatever you want to call it, the forces are all balanced, the object doesn't move. But there's a second rule that goes with normal forces. So normal forces must be perpendicular to the surface, or they're generally perpendicular to the surface that they're sitting on. So normal force is perpendicular to surface or object or whatever which is applying it. And that basically means that this case where the two are opposed, normal force and gravity are opposed, is a special case in which the surface that the object is sitting on is actually flat. That also means that if I were to rotate the plane, that I will no longer have a normal force that is purely vertical. It's no longer purely pointing in the opposite direction of gravity. Gravity would still, in this case, point straight downward, but the normal force would now point at some other direction. For what it's worth, this word normal is often used in mathematics to mean perpendicular. So that's why it must be perpendicular. That's where the name comes from. It's got to be perpendicular to the surface. So now we come to our inclined plane. So here's my inclined plane. I'm going to draw a little horizontal. Again, I place my object on the inclined plane. My object again has mass m. Again, if I was to draw a free body diagram for this mass m, I would have to say gravity acts downwards in this direction. But now my normal force has to be perpendicular to the plane. So it comes off in this direction like this. And so now we have to figure out how much force net is there. And there's two ways to do that. Basically, we want to do vector resolution somehow. One option for vector resolution is to do a polar, add these two in polar. Essentially what you'd find is that if you added these together in polar, so doing vector resolution in polar, you'd have your FG. I'm just going to draw my kind of dashed lines for my polar, or for my inclined plane. My Fn actually would be exactly like this. So here's Fn. And that means that my total, my sum of these two, which I'm going to draw here in blue, this is Fg plus Fn, which in the problem as drawn, if this is a frictionless surface, this would therefore be the sum of forces, or the net force in the problem. So now what we have to do is figure out what these two add to. Now again, you can draw everything to scale using a ruler and protractor. If you're told that this plane is inclined by some angle theta, you're usually told, theta will be 5 degrees or whatever. You can draw a horizontal line here. You can take a protractor out, draw another line that's at 5 degrees. You can essentially draw an arrow from mass that goes all the way down to where this horizontal line is and touches. You can draw a second arrow to scale that comes up and touches where this plane is, and then the resulting line right here from start of the first to end of the second, that will accurately be your sum of forces. And so now you can use the ruler to measure what the length of it is. The direction it'll turn out will always be parallel to this plane. So that's the polar method for resolving these. And again, I'm not doing this very thoroughly because it's a bit of a pain to do on the computer with the drawing pad. You can do it though, and it works, and if that's how you want to solve stuff on exams, go for it. Not very many people do, and if for some reason you end up taking the MCAT or some other test outside of my class where you have to know these things, then you may be looked at a little bit like an eccentric. But it does work. It will get you the right answer. So how do you do it with Cartesian coordinates? In other words, how can we break this up into an X and a Y? Well, one way to do it is to say the Y direction is up-down, the X direction is left-right, and therefore I have to somehow break up the normal force into an up-down and a left-right component. That method works okay, but it's not really the preferred option for an inclined plane. Instead, it's actually better to sort of rotate your coordinate axes. And so the rotated coordinate axis is draw a new set of coordinates, one parallel to the ramp, that will be your X, and one perpendicular to the ramp, that'll be your Y. Now, if I draw that same coordinate system over here, it would look like this. Okay? So here's X, here's Y. And what do you notice about that same coordinate system that I have drawn over here on my free body diagram where I've drawn my forces? Well, what you should notice is that the y-axis is parallel to the normal force. So with this new coordinate system, the normal force is entirely along y, and that also means if I draw over here that same coordinate system, that also means that the net force is entirely along x. Notice that the y-axis is still parallel to the normal force. Notice that the x-axis now parallels the net force. So this new coordinate system that I've made is sort of x is along the ramp, y is perpendicular to the ramp. Okay, but that means that we've got to now convert gravity into an x and a y component. Essentially, with this new axis, we could write the normal force is representable by 0x, comma, normal force along y. So it has only a y component. Gravity, on the other hand, Fg, does not have only a y component. It has an x and a y. And so we have to look and figure out what's the x and what's the y. Well, again, this right here was representing my gravity force. Fg is mg. And this right here is a right angle. Now if I draw another line over here, dash, 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 this is a right angle and I have a theta. And I notice that this right here is a similar triangle to the triangle that I've made here, which means that this angle right here and this angle right here have to be the same value. This has to be a theta. Now I use sine of theta is opposite over hypotenuse and cosine of theta is adjacent over hypotenuse to get that the force of gravity is mg sine of theta, comma, mg cosine of theta. In other words, the y component goes with sine theta and the x component goes with cosine theta. And again, that comes out of this triangle that I just drew using forces. So if I draw the triangle a little bit bigger here, this right here represents my gravity force. This right here would be my x component, and this right here would be my y component. So Fgx and Fgy. This right here is my angle theta, and this right here is my right angle. Okay, so these go with this triangle. Now if I want to get the sum of forces, I know that in the direction perpendicular to the ramp, I have no net force. That's another way of saying this object, this box, remains on the ramp as it slides down the ramp. It doesn't float off, it doesn't fall through, it just slides along. Okay, so the conditions for Newton's law will basically be this. In the x direction, I basically get m times g times sine of theta is mass times acceleration. And so therefore acceleration is g sine theta. On the other hand, in the y direction, I have m times g times cosine theta, downward, or negative word, plus the normal force is 0. And so that implies that the normal force is m times g times cosine theta. Okay, and those are kind of your two base equations for figuring out motion along a ramp. You have the x direction, which gives you the acceleration. You have the y direction, which gives the normal force. In a future video, I may further complicate this by adding in things like friction. But that's all that I wanted to cover in today's short video. So I hope you've learned a bit from it and understand this subject a little bit better. Thanks for watching.